October 25, 1944, USS Lexington, Philippine Sea. Fire Controlman First Class Thomas McKenzie adjusted the dials on his Mark 37 gun director as the general quarters alarm shrieked across the carrier's flight deck. Through his optical rangefinder, he tracked a formation of incoming aircraft, 12 Mitsubishi A6M Zero fighters approaching at 15,000 feet, their wings glinting in the afternoon sun. The radio crackled with urgent reports. Bogeys inbound, bearing 270 degrees, Angels 15, probable suicide attack. McKenzie's hands moved with practiced precision, feeding range and bearing data to the ship's 5-inch gun mounts below. What he didn't know was that the shells being loaded into those guns contained a revolutionary technology that would transform the mathematics of aerial warfare and drive Japanese pilots to admit their deepest fears about American devil shells that seemed to explode with supernatural accuracy. Before we jump back in, tell us where you're tuning in from, and if this story touches you, make sure you're subscribed, because tomorrow I've saved something extra special for you. The Pacific War had entered its most desperate phase. Emperor Hirohito's military commanders, facing inevitable defeat, had unleashed their most terrifying weapon: organized suicide attacks by pilots willing to die for their emperor. The Kamikaze, divine wind, represented Japan's final gamble to inflict such devastating losses on American naval forces that the United States would negotiate a conditional surrender rather than invade the Japanese home islands. Admiral Takejiro Onishi's special attack units had fundamentally changed the tactical equation of naval warfare. Traditional dive bombers and torpedo planes required skilled pilots who expected to return from their missions. Kamikaze attacks eliminated the need for pilot survival, allowing aircraft to be used as guided missiles with human brains providing terminal guidance systems impossible to jam or deceive. The mathematical advantages were terrifying. A conventional bombing attack might achieve a 10% hit rate against a maneuvering warship. Kamikaze pilots, willing to die in their attacks, could theoretically achieve hit rates approaching 50% by simply aiming their entire aircraft at the target and continuing their attack even after sustaining damage that would force conventional pilots to abort. American naval losses were mounting at unsustainable rates. At Leyte Gulf, kamikaze attacks had sunk or damaged 47 American vessels in a single day. The escort carrier USS St. Lo had been completely destroyed when a Zero fighter, piloted by Lieutenant Yukio Seki, crashed through her flight deck and detonated the ship's aviation fuel stores. The explosion killed 143 American sailors and demonstrated that even small kamikaze aircraft could destroy the largest warships. Preparing and narrating this story took us a lot of time, so if you are enjoying it, like this video, it means a lot to us. Now back to the story. Traditional anti-aircraft defenses were proving inadequate against suicide attacks. Standard time-fused shells exploded at predetermined altitudes, creating lethal fragmentation patterns designed to damage aircraft enough to force them away from their targets. But kamikaze pilots continued their attacks, even with mortal wounds, requiring direct hits or near misses close enough to physically destroy their aircraft before impact. The United States Navy needed a technological solution to a tactical problem that threatened to make amphibious operations impossible. Japanese commanders were planning Operation Kikusu, floating chrysanthemum, massive coordinated kamikaze attacks involving thousands of suicide aircraft that would target American invasion fleets approaching Okinawa and the Japanese home islands. The answer lay in a classified weapons development program that had begun 3 years earlier in a Johns Hopkins University laboratory in Maryland. Dr. Merle Tuve and his team of physicists and engineers had been working on a proximity fuse, a shell that would detonate automatically when it came close to its target, rather than relying on mechanical timing mechanisms or direct impact. The VT fuse, variable time, though military personnel called it the very top secret fuse, represented the convergence of multiple revolutionary technologies. A miniature radar transmitter, small enough to fit inside an artillery shell. A receiver capable of detecting radio waves reflected from aircraft surfaces. Electronic circuits that could distinguish between target echoes and ground reflections. and an explosive trigger reliable enough to function after being fired from a naval gun at accelerations exceeding 20,000 times the force of gravity. The physics were elegant and deadly. Each VT-fused shell transmitted continuous radio waves at a frequency of 180 MHz as it flew toward its target. When these waves struck an aircraft, they reflected back to the shell's receiver. As the distance decreased, the strength of the reflected signal increased exponentially. When the signal reached a predetermined threshold, indicating the shell was approximately 70 feet from a target, the fuse triggered detonation. Unlike time fuses that created random explosion patterns, VT fuses guaranteed that every shell would detonate at the optimal distance to damage or destroy enemy aircraft. The lethal radius of a 5-inch high explosive shell was approximately 60 feet. VT fuses ensured that every projectile detonated within this kill zone, transforming anti-aircraft gunnery from an art based on estimation and experience into a mathematical certainty. Production statistics revealed the scale of American industrial commitment to this new technology. By October 1944, American factories were manufacturing 40,000 VT fuses per day. Each fuse contained over 100 electronic components, including vacuum tubes smaller than a pencil eraser, capacitors the size of rice grains, and antenna elements made from wire thinner than human hair. The precision required in manufacturing made VT fuses more complex than contemporary radio receivers, yet they had to function reliably after being subjected to the violent acceleration of naval gunfire. Lieutenant Commander James Big Jim Patterson commanded the USS Lexington's anti-aircraft battery, 16 5-inch dual-purpose guns arranged in 8 twin mounts around the carrier's superstructure. A former mathematics teacher from Nebraska, Patterson understood that successful anti-aircraft defense was ultimately about probability calculations and timing precision. Each gun could fire 22 rounds per minute. With VT fuses, every round had a theoretical 85% probability of destroying or seriously damaging any aircraft passing within 140 feet of its explosion point. His gunnery teams had been practicing VT fuse tactics for months, but the technology remained so classified that most gunners didn't understand how the new shells achieved their remarkable accuracy. They simply knew that targets which previously required 60 to 80 rounds to destroy could now be eliminated with 8 to 10 VT-fused projectiles. Fire Controlman McKenzie had studied the mathematical principles of the Mark 37 fire control system until he could calculate firing solutions in his head. Wind speed and direction affecting projectile flight paths, target course and speed for lead calculations. The difference between hitting and missing often came down to fractions of degrees in gun elevation and seconds of timing in projectile flight. But VT fuses had simplified the mathematics considerably. Traditional time fuses required precise calculation of target altitude, speed, and course to determine when shells would detonate. VT fuses eliminated altitude calculations entirely. The shell would automatically explode when it came close to any target, regardless of altitude variations. Aboard the Japanese aircraft carrier Zuikaku, Lieutenant Commander Hiroshi Nakamura briefed his Kamikaze pilots on American defensive improvements. Intelligence reports from surviving pilots described American anti-aircraft fire of unprecedented accuracy, shells that seemed to explode exactly when they came close to Japanese aircraft, rather than at random altitudes based on mechanical timing. Petty Officer First Class Kenji Yamamoto had survived 3 kamikaze missions, extraordinary for a program where pilots were expected to die on their first attack. His aircraft had been damaged by American gunfire on each mission, but he had managed to crash land on Japanese-held islands and return to duty. His reports to intelligence officers described American devil shells that exploded with supernatural timing, creating lethal fragmentation patterns that seemed specifically designed to intercept kamikaze attacks. Japanese naval intelligence had begun collecting shell fragments from American anti-aircraft fire, searching for clues to explain the sudden improvement in American gunnery accuracy. What they found were electronic components unlike anything in Japanese weapons technology: miniature vacuum tubes, precision capacitors, and antenna elements that suggested some form of radio-controlled explosive device. The first large-scale test of VT-fuse technology against kamikaze attacks came during the Battle of Leyte Gulf on October 25, 1944. Admiral Takeo Kurita's center force had been decimated by American submarine and air attacks, but Admiral Onishi's special attack units remained intact and ready for coordinated suicide strikes against the American invasion fleet. At 0645, radar operators aboard the USS Lexington detected the first wave of kamikaze attacks. 18 Zero fighters and 6 Nakajima B-6N torpedo bombers, approaching from multiple directions at altitudes between 8,000 and 12,000 feet. The formation's tactical coordination was unlike anything American forces had previously encountered, each aircraft approaching from a different bearing, making traditional defensive fire patterns ineffective. Lieutenant Commander Patterson ordered his gun crews to commence firing at maximum range. Traditional doctrine called for holding fire until targets closed to 6,000 yards to ensure accuracy with time-fused shells. But VT fuses allowed effective engagement at ranges exceeding 10,000 yards, creating defensive fire zones that stretched far beyond anything Japanese pilots had previously experienced. The mathematical advantages were immediately apparent. McKenzie's fire control solutions put the first VT-fused salvo directly into the path of the lead kamikaze formation. 4 shells exploded simultaneously as they detected nearby aircraft, creating a lethal fragmentation pattern that destroyed 3 Zero fighters and severely damaged 2 others. The damaged aircraft attempted to continue their suicide attacks but crashed into the ocean short of their targets. From the Japanese perspective, the engagement was nightmarish. Warrant Officer Saburo Tanaka, leading the first attack wave, watched his wingmen disappear in explosions that seemed to track his aircraft with impossible precision. Traditional American anti-aircraft fire had been predictable, time-fused shells that exploded at consistent altitudes, creating fragmentation patterns that could be avoided through radical maneuvering. But these new American shells detonated exactly when they came close to Japanese aircraft, as if they possessed some form of intelligence or guidance system. Tanaka's shell shuddered as shrapnel from a near-miss punched holes through his wings and engine cowling. His engine began streaming oil and losing power, but he continued his dive toward the American carrier below. The engagement data from October 25, 1944 revealed the revolutionary impact of VT-fused technology on anti-aircraft warfare. American gunners fired 347 rounds during the 22-minute battle. Traditional time-fused shells would have achieved an estimated 12 to 15 aircraft kills based on previous engagement statistics. VT-fused shells destroyed or damaged 31 Japanese aircraft, a hit rate improvement of over 400%. The psychological impact on surviving Japanese pilots was equally significant. Post-battle interrogations of captured aircrews revealed widespread fear about American radio shells that seemed to pursue Japanese aircraft with supernatural accuracy. Pilot reports described explosions that occurred exactly when American shells came close to their targets, regardless of altitude or maneuvering attempts. Engineering Officer Commander Robert Hayes had been analyzing VT-fused performance data throughout the Pacific campaign. His calculations revealed that the new proximity fuses had fundamentally changed the mathematical equation of aerial warfare. Traditional anti-aircraft guns required an average of 2,800 rounds to destroy a single enemy aircraft. VT-fused guns achieved kills with an average of 150 rounds, a 95% improvement in ammunition efficiency. The implications extended far beyond individual engagements. American ammunition production could support much longer campaigns, with VT fuses requiring significantly fewer rounds per target destroyed. Logistical advantages that would prove decisive as the Pacific War entered its final phase, with massive kamikaze attacks planned against American invasion forces.
But the human cost of this technological advantage was equally apparent. Japanese pilots were dying at unprecedented rates, often in aircraft that disintegrated around them as VT-fused shells created lethal fragmentation patterns impossible to evade through maneuvering. McKenzie found himself counting enemy aircraft destroyed with the same mechanical precision he applied to fire control calculations. But each tally represented human lives ended by technology those pilots couldn't understand or counter. Japanese intelligence efforts intensified as reports of American super shells spread throughout kamikaze units. Lieutenant Commander Nakamura had been tasked with developing counter-tactics against whatever new weapon system the Americans were employing. His analysis of pilot reports suggested that American anti-aircraft shells were somehow detecting Japanese aircraft and timing their explosions for maximum effectiveness. The technical implications were troubling for Japanese military planners. If American forces had developed proximity-fused artillery shells, similar technology might be applied to other weapon systems, naval gunfire, coastal defense batteries, even anti-personnel weapons. The technological gap between Japanese and American military capabilities was widening at an alarming rate. November 1, 1944, brought the largest coordinated kamikaze attack yet attempted against American naval forces. Operation Sho Ichigo called for 650 suicide aircraft to strike the American invasion fleet off Leyte simultaneously, overwhelming defensive systems through sheer numbers. Admiral Onishi had calculated that even with improved American anti-aircraft effectiveness, sufficient kamikaze aircraft could penetrate defensive fire to sink or damage 30-40 American vessels. The mathematics seemed to favor the Japanese attackers. American task forces typically carried 800 to 1,200 anti-aircraft guns of various calibers. Even with VT fuses, engagement time against individual targets averaged 45 seconds. Simple arithmetic suggested that 650 simultaneous attacks would overwhelm any defensive system through numerical superiority. But VT fuse technology created tactical advantages that Japanese planners hadn't anticipated. The ability to engage targets at extreme range meant that American gunners could begin shooting at kamikaze formations while they were still 15-20 miles from their targets. Extended engagement time allowed multiple firing passes against each target, dramatically increasing kill probabilities. Radar-directed fire control provided continuous tracking data that kept VT-fused shells accurately aimed even when targets maneuvered violently. Japanese pilots found that their traditional evasion tactics, sudden altitude changes, radical turns, and unpredictable approach patterns had become ineffective against shells that automatically adjusted their detonation timing based on proximity to targets. The engagement began at 09:30 when the first wave of 85 kamikaze aircraft approached Task Force 38 from the northeast. American radar operators tracked the formation from 120 miles away, providing gun crews with precise bearing and range data long before visual contact was possible. Patterson's battery began firing at 09:47, launching VT-fused shells toward targets still invisible to the naked eye. McKenzie watched through his rangefinder as the first American salvos detonated among the approaching Japanese formation. Unlike previous engagements where anti-aircraft fire created random explosion patterns that damaged some aircraft while missing others entirely, VT fuses ensured that every shell exploded at the optimal distance to maximize target destruction. The mathematical precision was devastating. Each 5-inch shell contained 14 pounds of high explosives that created lethal fragmentation patterns extending 120 feet in all directions. VT fuses guaranteed that these explosions occurred exactly when they would cause maximum damage to nearby aircraft. Japanese pilots found themselves flying into carefully orchestrated killing zones where every explosion was positioned for optimal lethality. American tactical doctrine evolved rapidly as VT fuse effectiveness became apparent. Traditional anti-aircraft formations had been designed around the limitations of time-fused shells that exploded at predetermined altitudes. Guns were positioned to create overlapping fire zones where multiple weapons could engage single targets, compensating for the low hit probability of individual shells. VT fuses eliminated the need for overlapping fire patterns by ensuring that every shell had a high probability of destroying its target. This allowed gun crews to engage multiple targets simultaneously rather than concentrating fire on single aircraft. The tactical advantage was enormous. American ships could now deal with coordinated attacks that would previously have overwhelmed their defensive capabilities. Fire control procedures were revolutionized as gunners learned to trust VT fuse technology. McKenzie's training emphasized rapid target acquisition and immediate engagement rather than careful aim and patient firing. The VT fuses would handle accuracy. Human operators needed to focus on identifying targets and maintaining continuous fire until threats were eliminated. The psychological impact on American gunners was equally significant. Previous anti-aircraft engagements had been exercises of frustration. Hundreds of rounds fired with minimal visible results. VT fuses provided immediate feedback as targets exploded spectacularly when shells detonated nearby. Gun crews developed confidence in their weapons that translated into more aggressive tactics and sustained fire rates. Japanese military intelligence had been analyzing captured VT fuse fragments since August 1944, but the technology remained largely incomprehensible to engineers familiar only with mechanical timing devices and contact fuses. The electronic components suggested some form of radio-controlled system, but the miniaturization required to fit such equipment inside artillery shells seemed impossible with Japanese manufacturing capabilities. Technical analysis teams led by Professor Yoshio Nishina at the Imperial Navy's Research Institute had identified key components, vacuum tubes, capacitors, antenna elements, but couldn't determine how they functioned as an integrated system. Japanese electronics manufacturing was years behind American capabilities, particularly in miniaturization techniques required for military applications. Counter-tactics development focused on what Japanese engineers did understand. If American shells were using radio waves to detect targets, perhaps electronic jamming equipment could interfere with their operation. Experimental transmitters were installed on some Kamikaze aircraft, broadcasting signals on frequencies that might disrupt American proximity fuses. The results were disappointing. VT fuses operated on frequencies and used signal processing techniques that Japanese jamming equipment couldn't effectively target. Worse, the radio transmitters added weight to Kamikaze aircraft and reduced their already limited range and maneuverability.
The psychological warfare implications were significant. Kamikaze attacks required pilots willing to face certain death, but they also required confidence that their sacrifice would achieve military objectives. Reports of American Devil shells that made successful attacks nearly impossible began undermining the spiritual foundations of the special attack program. Morale assessments from kamikaze training units revealed growing reluctance among new pilots to volunteer for suicide missions. Where recruitment had previously exceeded available aircraft, intelligence reports now described shortfalls in pilot volunteers and increased desertion rates from special attack squadrons. Japanese military censors began restricting pilot communications to prevent demoralization from spreading to other units. Letters home were heavily edited to remove references to American superweapons or impossible defensive accuracy. But word spread through informal channels as wounded pilots recovered in Japanese hospitals described encounters with American shells that seemed to target individual aircraft with precision impossible using traditional weapons. Admiral Nimitz's Pacific Fleet intelligence staff had been analyzing kamikaze attack patterns and success rates since the program began. Early engagements showed Japanese suicide attacks achieving hit rates approaching 40% against American naval targets. By November 1944, after VT fuses had been widely deployed, kamikaze success rates had dropped to less than 15%. The mathematical progression was clear and decisive.
Japanese planners had calculated that coordinated kamikaze attacks could sink or damage enough American vessels to make amphibious operations prohibitively expensive. But VT-fuse technology had fundamentally altered those calculations by making individual suicide attacks much more likely to fail. Strategic planning implications extended to the highest levels of American command. General MacArthur's invasion plans for the Philippines and eventual assault on Japan itself had been premised on acceptable casualty rates during amphibious operations. Kamikaze attacks threatened to make such casualties unacceptable to American public opinion and political leadership. VT fuses had restored the tactical advantage to defensive forces by making it possible to destroy attacking aircraft before they could reach their targets. This technological edge would prove critical as Japanese commanders planned even more massive kamikaze operations for the defense of Okinawa and the home islands. Japanese intelligence services had been attempting to acquire VT-fuse technology through espionage networks in the United States and captured equipment analysis in the Pacific. The technical challenge was enormous. Even with complete examples of American proximity fuses, Japanese industry lacked the manufacturing capabilities to produce similar devices. Vacuum tube production in Japan was limited to relatively large devices suitable for radio receivers and transmitters. The miniaturization required for VT fuses demanded precision manufacturing techniques and materials that weren't available to Japanese military contractors. Electronic components that American factories produced by the millions were beyond Japanese manufacturing capacity. Counterintelligence efforts by American forces included deliberate disinformation about VT fuse technology. Captured documents were altered to suggest that proximity fuses required rare materials unavailable to Japanese industry. False technical specifications were planted in locations where Japanese agents might discover them, leading Japanese researchers down unproductive development paths. The deception campaign extended to battlefield operations where American forces made efforts to prevent intact VT fuses from falling into Japanese hands. Gun crews were instructed to destroy any shells that failed to detonate, and recovery operations were mounted to collect VT fuse fragments before Japanese forces could analyze them.
March 18, 1945. Imperial Japanese Navy Headquarters, Tokyo. Admiral Suemu Toyoda studied the intelligence reports spread across his mahogany desk, each document revealing the mounting catastrophe facing Japanese naval aviation. Kamikaze success rates had plummeted from 40% in October to barely 12% by February. American anti-aircraft fire had become so devastatingly effective that suicide pilots were describing their missions as flying into walls of exploding steel. But Emperor Hirohito's final directive was absolute. Every available aircraft would be committed to Operation Tengo, the defense of Okinawa with 10,000 kamikaze planes in coordinated mass attacks that would either destroy the American invasion fleet or exhaust Japan's remaining air power in one decisive gamble. The strategic mathematics were stark. American forces were assembling the largest amphibious invasion fleet in Pacific War history, 1,300 vessels carrying 550,000 assault troops for the conquest of Okinawa. Intelligence estimates suggested that sinking 200 to 300 American ships would force a negotiated peace rather than continued advance toward the Japanese home islands. Operation Tengo would commit every trainer, obsolete fighter, and converted civilian aircraft to achieve these numbers through organized mass suicide. Vice Admiral Matome Ugaki, commanding the 5th Air Fleet, had been tasked with coordinating the largest aerial suicide attack in military history. His staff calculated that 10,000 aircraft attacking simultaneously would overwhelm any defensive system through pure numerical superiority. Even with improved American anti-aircraft effectiveness, sufficient kamikaze planes would penetrate defensive fire to achieve strategic objectives. But American technological advantages had progressed far beyond what Japanese intelligence understood. VT fuse production had reached 100,000 units per day by March 1945.
Every American anti-aircraft gun, from 5-inch naval weapons to 90mm Army batteries, now fired proximity-fused ammunition exclusively. The mathematical equation that made mass kamikaze attacks theoretically viable was about to encounter technological reality. USS Bunker Hill, Task Force 58, Philippine Sea. Captain George Seitz watched as ammunition handlers loaded the final VT-fused rounds into her ship's magazine spaces. Each 5-inch shell represented months of precision manufacturing, vacuum tubes tested to survive 20,000 G acceleration, capacitors smaller than aspirin tablets, antenna elements calibrated to detect aircraft at exactly 70 feet. The carrier's 16 dual-purpose guns now carried 4,000 proximity-fused rounds, enough sustained firepower to engage continuous targets for 6 hours without resupply. Gunnery Officer Commander Michael O'Brien had been analyzing VT-fused performance data from previous engagements, refining tactical doctrine based on mathematical certainties rather than traditional naval gunnery experience. His calculations revealed that American task forces could now generate defensive fire zones extending 25 miles from protected vessels. Any aircraft attempting to penetrate these zones faced mathematical destruction rates exceeding 90% before reaching attack positions. The technological integration was unprecedented in naval history. Radar systems provided target detection at 150-mile ranges. Electronic fire control computers calculated shooting solutions automatically. VT fuses ensured that every shell detonated at optimal distance from targets. Human operators had become supervisors of automated killing systems that functioned with machine precision. Fire Controlman First Class David Chen aboard the USS Yorktown had been tracking American gunnery improvement statistics since VT fuses entered service. Traditional anti-aircraft guns required 2,800 rounds to destroy single targets. Current effectiveness ratios showed 85 VT-fused rounds per aircraft destroyed, a 97% improvement in ammunition efficiency that translated into sustained defensive capability against mass attacks. Kanoya Air Base, Kyushu, March 25, 1945, Captain Rikihei Inoguchi addressed 200 kamikaze pilots assembled in the base's largest hangar. These men represented Japan's final aviation reserve, flight instructors, academy cadets, and volunteer civilians with minimal flight training. Their aircraft were equally desperate: obsolete fighters, training planes, and converted civilian aircraft with 500-pound bombs for suicide attacks. The briefing revealed the hopeless mathematics facing Japanese planners. American invasion forces approaching Okinawa included 16 aircraft carriers protected by over 400 anti-aircraft guns firing improved ammunition. Intelligence reports suggested that American defensive fire had become so accurate that individual aircraft faced destruction probabilities exceeding 85% during attack approaches. Lieutenant Yasuo Kuwahara, a former flight instructor with 2,000 hours experience, studied reconnaissance photographs of American task forces. The images showed defensive formations designed around technological capabilities that Japanese forces couldn't match. Ships positioned to provide overlapping radar coverage and mutually supporting anti-aircraft fire. Gun batteries that could engage targets simultaneously rather than concentrating fire on individual threats. Traditional kamikaze tactics, low-altitude approaches to avoid radar detection, high-speed dives to minimize engagement time, had become obsolete against American proximity fuses that functioned regardless of target altitude or approach speed. Japanese pilots were being asked to penetrate defensive systems specifically designed to counter their attack methods, using weapons that eliminated human skill advantages through automated accuracy. The spiritual dimension of kamikaze operations was equally compromised by reports of American superweapons. Pilots who had volunteered for suicide missions, believing their sacrifice would achieve meaningful military objectives, now faced evidence that individual attacks had minimal success probability. The mathematical certainty of death without corresponding certainty of target destruction undermined the philosophical foundations of organized suicide warfare. Operation Kikusui-1 commenced at dawn with 355 kamikaze aircraft launching coordinated attacks against American forces off Okinawa. Japanese planners had calculated that simultaneous attacks from multiple directions would saturate American defensive capabilities, allowing sufficient aircraft to penetrate and sink major vessels. The mathematical theory assumed that American guns required 45 seconds engagement time per target and could be overwhelmed by numerical superiority. Admiral Richmond Kelly Turner's amphibious force had been expecting mass kamikaze attacks and had positioned his ships in defensive formations optimized for VT fuse effectiveness. Radar picket destroyers extended detection ranges to 200 miles while providing early warning for coordinated defensive fire. The mathematical reality was that American forces could begin engaging Japanese formations while they were still 150 miles from their targets.
The engagement began at 6:30 when radar operators detected the first Japanese formations approaching from the northeast. USS Laffey, positioned as radar picket 30 miles from the main invasion fleet, began firing VT-fused rounds at targets still invisible to optical systems. The destroyer's 5-inch guns achieved target acquisition at 18,000 yards and maintained continuous fire as Japanese aircraft approached. Gunner's mate Second Class Robert Johnson had been tracking targets through his Mark 37 Director for 12 minutes before visual contact was possible. VT fuses allowed engagement at extreme ranges where traditional time-fused shells would have been ineffective due to target maneuvering unpredictability. Proximity fuses eliminated the need to calculate exact detonation timing by automatically triggering when shells approached within lethal range. The results were immediately apparent. Johnson's first salvo of 8 VT-fused rounds destroyed 3 Japanese aircraft and damaged 2 others at ranges exceeding 15,000 yards. Traditional anti-aircraft doctrine would have held fire until targets closed to 8,000 yards, allowing Japanese pilots to approach within effective attack range before encountering defensive fire. Japanese formations approaching American defensive zones encountered killing fields of unprecedented lethality. Every American ship fired continuously at maximum rates, creating overlapping explosion patterns that made survival mathematically impossible. VT fuses ensured that 85% of all rounds fired detonated at optimal distances from targets, transforming anti-aircraft gunnery from probabilistic engagement into certain destruction. Captain Katsushige Takada, leading a formation of 18 Zero fighters toward USS Bunker Hill, watched his squadron disintegrate under American fire that seemed personally targeted at each aircraft. Traditional anti-aircraft fire created random explosion patterns that skilled pilots could evade through maneuvering. But these American shells detonated exactly when they came close to Japanese aircraft, making evasion impossible through pilot skill or tactical innovation. The mathematical progression was inexorable. Takada's formation faced engagement by 64 American guns firing 1,400 rounds per minute. Each round had 85% probability of destroying any aircraft within 140 feet of its detonation point. Simple arithmetic revealed that Japanese aircraft faced certain destruction within 3–4 minutes of entering American defensive zones. Electronic warfare attempts by Japanese forces proved equally ineffective. Experimental radio jamming equipment installed on lead aircraft was designed to interfere with American proximity fuses by broadcasting signals on suspected frequencies. But VT fuses operated on multiple frequencies with signal processing sophisticated enough to distinguish between target echoes and electronic interference. The technological gap had become insurmountable. American proximity fuses represented 3 years of advanced research by leading electronics manufacturers. Japanese industry lacked the precision manufacturing capabilities and miniaturization techniques required to produce similar devices. Even with captured examples of VT fuses, Japanese engineers couldn't reverse engineer production methods for components beyond their industrial capacity.
Seaman First Class William Murphy aboard USS Aaron Ward had been firing continuously for 90 minutes as Japanese aircraft attempted to penetrate his ship's defensive zone. His 5-inch gun had expended 340 VT-fused rounds, destroying 27 confirmed targets with mathematical precision that would have been impossible using traditional ammunition. But each explosion represented human lives ended by technology those pilots couldn't understand or counter. Murphy's gun crew worked with mechanical efficiency, loading shells and adjusting aim while Japanese pilots died in aircraft that exploded around them. The human element of warfare had been reduced to mathematical calculations, range, bearing, and proximity-fused detonation timing. Individual courage and skill had become irrelevant factors in combat determined by technological superiority. Lieutenant Iwao Matsuo, one of the few Japanese pilots to survive the first day's attacks, described the engagement in terms that revealed complete demoralization. American shells followed our aircraft like hunting dogs. No matter how we maneuvered, they exploded exactly when they came close enough to kill us. Our training and experience meant nothing against weapons that seemed to think. His testimony influenced subsequent Japanese tactical planning as commanders realized that traditional pilot training was obsolete against American proximity fuses. Evasive maneuvering, altitude changes, and approach variations had no effect on shells that automatically detonated when they detected nearby aircraft. The accumulated wisdom of aerial combat had been rendered meaningless by electronic automation. April 12, 1945 brought the second massive kamikaze attack, with 380 suicide aircraft attempting coordinated strikes against American naval forces. Japanese planners had analyzed the failure of the first operation and concluded that simultaneous attacks from all directions might overwhelm American defensive capabilities through sheer numerical density. The mathematical theory was sound, but ignored technological realities. American radar systems provided 360-degree coverage with electronic fire control computers capable of engaging multiple targets simultaneously. VT fuse production had increased to support sustained defensive fire at maximum rates without ammunition shortages. USS Intrepid's anti-aircraft battery demonstrated the evolution of American defensive doctrine. Captain Joseph Bolger's gun crews engaged 47 separate targets during the 4-hour battle, firing 892 VT-fused rounds with 89% effectiveness ratio. Traditional anti-aircraft operations would have required concentration of fire on individual targets. Proximity fuses allowed simultaneous engagement of multiple threats with confidence that each shell would detonate at optimal distance from any nearby aircraft. The psychological impact on Japanese pilots was catastrophic. Intercepted radio transmissions revealed widespread panic as kamikaze formations encountered defensive fire of impossible accuracy. Pilots described American shells that hunted their aircraft and exploded with perfect timing. The spiritual certainty required for suicide attacks was being undermined by encounters with weapons that seemed supernatural in their effectiveness. Japanese military censors began restricting communications from kamikaze units to prevent demoralization from spreading throughout remaining aviation forces. But statistical reality couldn't be hidden. Attack success rates had dropped to 8%, while pilot survival rates approached 0. The mathematical equation that made organized suicide attacks viable had been destroyed by American technological advantages. Japanese technical intelligence had been desperately attempting to understand American proximity fuse technology since captured examples became available in late 1944. Professor Hideki Yukawa's team at Kyoto Imperial University had identified key components but couldn't determine how miniaturized radar systems functioned inside artillery shells.
The manufacturing challenge was overwhelming. VT fuses required vacuum tubes 1/10 the size of standard Japanese electronics, precision capacitors with tolerances measured in thousandths of inches, and antenna elements made from materials unavailable to Japanese industry.
Even with complete technical specifications, Japanese production capabilities were insufficient to manufacture similar devices. Counter-development efforts focused on alternative approaches that might neutralize American proximity fuses. Experimental shells filled with metallic chaff were designed to create false radar returns that might trigger premature detonation. Electronic noise generators attempted to jam VT fuse frequencies. None proved effective against American signal processing techniques that distinguished between aircraft targets and countermeasures. The technological disparity extended beyond individual weapons to entire industrial systems. American factories were producing proximity fuses using precision manufacturing techniques and quality control methods that Japanese industry couldn't match. Even with unlimited resources and time, Japanese technological capabilities were years behind American achievements in electronics miniaturization and mass production. June 21, 1945. The 10th and final mass kamikaze attack involved 400 aircraft in a desperate attempt to damage American forces enough to force negotiated peace before invasion of the Japanese home islands. By this stage, Japanese aviation had been reduced to training aircraft piloted by teenagers with minimal flight experience facing American defenses that had achieved technological perfection. Admiral Ugaki's final briefing to remaining kamikaze pilots acknowledged the mathematical hopelessness of their situation. American anti-aircraft effectiveness had reached 94% destruction rates against individual targets. Proximity fuses had eliminated every tactical advantage previously enjoyed by suicide attackers. The mission was no longer about military effectiveness, but about demonstrating Japanese spiritual determination in the face of overwhelming technological superiority. The engagement demonstrated the complete transformation of aerial warfare. American gun crews aboard USS Missouri fired 1,247 VT-fused rounds during the 6-hour battle, destroying 73 Japanese aircraft without suffering significant damage. Fire control systems functioned with such precision that human operators served primarily as supervisors of automated destruction processes. The mathematical reality had become undeniable. Japanese kamikaze operations had lost their tactical viability against American proximity fuses. Individual aircraft faced near-certain destruction regardless of pilot skill, tactics, or spiritual determination. The age of human factors determining combat outcomes had ended, replaced by technological superiority that made traditional courage irrelevant. VT fuse technology had fundamentally altered the strategic balance of Pacific warfare. Japanese planners had calculated that coordinated kamikaze attacks could inflict sufficient casualties on American naval forces to make invasion of the home islands prohibitively expensive. Proximity fuses had eliminated this strategic option by making individual suicide attacks mathematically certain to fail. American casualty rates during the Okinawa campaign were significantly lower than projected due to VT fuse effectiveness against kamikaze attacks. Naval losses that might have reached 200-300 vessels were limited to 36 ships sunk and 368 damaged. The technological advantage had preserved American combat capability while exhausting Japanese aviation reserves in futile attacks. The implications extended to post-war military planning. Every major navy began developing proximity fuse technology based on captured German and American examples. The age of manned aircraft operating in defended airspace without electronic countermeasures had ended. Future aerial warfare would require sophisticated electronic systems to survive increasingly automated defensive weapons. Post-war analysis revealed that VT fuses had achieved the most significant improvement in weapons effectiveness since the adoption of rifled artillery. Traditional anti-aircraft guns required 2,800 rounds per target destroyed. Proximity-fused weapons achieved kills with 150 rounds per target, a 95% improvement that transformed defensive warfare mathematics. The human cost of this technological revolution was staggering. Over 4,000 Japanese pilots died in kamikaze attacks during the Okinawa campaign, representing not just immediate casualties but the destruction of irreplaceable flying experience and training. Each pilot required years of instruction and combat experience to achieve effectiveness. American losses during the same period were primarily material rather than personnel. Industrial implications were equally significant. American proximity fuse production had required development of entirely new manufacturing techniques for precision electronics. These innovations would drive post-war advances in civilian electronics, radar systems, and eventually computer technology. The war had accelerated American technological development by decades. Surviving Japanese pilots described encounters with VT-fused anti-aircraft fire in terms that revealed complete psychological breakdown. Warrant Officer Saburo Sakai, one of Japan's most experienced fighter pilots, wrote, "American shells seemed to possess evil intelligence. They followed our aircraft and exploded exactly when they could kill us. No amount of training or courage could overcome weapons that eliminated human skill through mechanical precision." His testimony influenced post-war Japanese military analysis as officers tried to understand how technological superiority had rendered traditional military virtues obsolete. The spiritual foundations of Japanese military doctrine, emphasis on willpower, sacrifice, and individual determination, had been made irrelevant by American weapons that functioned with mathematical certainty regardless of enemy courage or skill. American perspectives were equally revealing. Gunner's Mate Johnson wrote to his family, "We're not really fighting pilots anymore, we're operating machines that kill automatically. The Japs are brave men, but bravery doesn't matter against fuses that detonate exactly when they're supposed to. It feels more like industrial work than combat." His observations captured the fundamental transformation of warfare from human contest to technology competition. Individual courage, tactical innovation, and combat experience had become secondary factors in conflicts determined by industrial capacity and scientific advancement. The success of VT fuses against kamikaze attacks marked the end of an era where individual skill and determination could overcome technological disadvantages. Japanese pilots who had dominated Pacific skies through superior training and tactical innovation found themselves helpless against American weapons that eliminated human factors through automated accuracy. Strategic planning for future conflicts would be based on technological capabilities rather than traditional military virtues. The side with superior electronics, precision manufacturing, and automated weapon systems would possess decisive advantages regardless of personnel quality or spiritual determination. The age of technological warfare had begun. American military leaders recognized that VT-fuse technology represented only the beginning of an electronics revolution in warfare. Radar-guided missiles, automated fire control systems, and eventually computer-directed weapons would continue the transformation from human-centered to technology-centered military operations.